a good way there, but not fully yet. Regular schedule for everything this week. I do anticipate having my own office hours on the advised schedule, recitations as usual. As you know, the second problem set is set for Friday night. As you saw from my email, just with the difficulty in getting mastering set up in time, I'm just bringing this back to the regular Thursday night deadline, which will be increased to the third problem set. The videos from class. How many of you use YouTube for those videos? Okay. At some point I'm going to ask someone expert for help. So the videos from this course should be up later today. As you know, when I mentioned this on Thursday last week, it turned out apparently you can have the most 2 channels. So in the process of trying to clean that up, I apparently deleted all of them. So I'll be starting afresh this afternoon. I'm amazed that YouTube, and I guess it's now Google, is as user unfriendly as it is, at least for an old person like me. Anyway, they'll be up later today. Lecture notes are mostly there. The problem set solutions, at least the first one, are up in the coursework. So pretty much close to on track, but not quite. Last thing I need to say is, some of you took a makeup final exam. I got those back on Friday. Still grading those, and at that point, I will, obviously, for those of you impacted by that, will be in touch with you, but it's also on that schedule that I still finally hope to get back to them. Those of you who had questions about the regular final exam and course grades, so I know you've been patient about that. Please just be a little bit longer, wait for a little bit longer on that. Okay, what are we covering today? So continuing our kinetic theory exploration, that was the primary result of Thursday, a very important one. Here it is. So we're going to start from that and see how we can fold that into what we know already, and in particular what happens when we fold it back into the ideal gas equation, start to gain some insights. As you know, in the derivation of this result, we basically took a sort of average speed distribution of all the atomic or molecular constituents in our gas. And that's the RMS speed that you see in that expression. That's fine, helps us get a good way of understanding the microscopic behavior of these gases. But what we're also going to do is come back and be a little bit more realistic and look at an actual velocity or speed distribution for the constituents in the gas. Because of course they are not all at the average speed. It's a large statistical ensemble. So we'll explore that a little bit. We won't go into it at least we won't derive it. There's a fair amount of technical stuff in today's class, which one, of course, can derive, but we don't need to. So we'll basically just talk about the result and what the implications of that are. We'll talk briefly about the mean free path of the constituents in one of these gases, how that might relate to some physical quantities, and then we're going to turn our attention back to specific heats and see how what we learn from this microscopic picture can inform our understanding of specific heats. That should take us through the end of the day. Thursday's class we're going to move on and talk about true thermodynamical processes. So I'm not going to say any more about that, I think, for now. So here's the result we ended up with on Thursday last week. Let me just remind you the salient features. Remember, this is taking a very idealized picture of these gases. They're relatively dilute. The constituents just collide with each other on the walls of whatever container they're in, but otherwise they're non-interacting. So what drops out of all of this is a fairly simple result. Macroscopic parameters, pressure and volume, fine. And then what we see most crucially is the dependence of the pressure on the square of the root mean square of the root mean square, so that means the root mean. The velocity of the constituents, okay? And of course some dependence on how much stuff we have, how much, and what the mass of the particular constituents are. So does it make sense? Yeah, I think so. You know, with this picture in mind now, it probably makes sense that as the speed of these constituents goes up, so does the pressure. It turns out it's a quadratic dependence. Okay? So that's where we left off on Thursday last week. So let's pick up from there and see what more we can learn from this. So first thing is, as you've seen a little bit, we've been going back and forth between counting on a molar basis and counting on a molecular basis. Equivalent is just a question of convenience maybe and a little bit of insight. So let me just add a different way of expressing this on a molecular basis rather than on a molar basis. I'm just going to recall for you the two important relationships you'll see us going back and forwards with these changing variables throughout our thermodynamics stuff. I'm just making sure I got this right. That makes more sense. So those are the two sort of relationships that we are often going back and forth between. So this is the ideal gas constant, sort of on a molar basis, then the Boltzmann constant on a molecular basis, Avogadro's number. There's the back and forth there. And then of course down here, again, Avogadro's number kicks in, is the relationship between the individual constituent mass and the molar mass, okay? So we're just basically counting on the either molecular or molar level. And so if I want to convert this to looking at the molecular basis rather than the molar basis, let me just make sure I got this right. I'm going to now just fold this back into the ideal gas equation. So let's come back and recall the ideal gas. PV equals nRT on the molar basis. So I'm going to do a substitution here and then come back with this. So if we take this and rearrange a little bit, we will first off find that I can write that P equals now, so this is nRT V. I'm doing the substitution from here. I get N molar mass V RMS squared over 3V. And so eventually, doing a comparison here, I've got N and V cancelling from both of these. So just compare this and this. And what it gets me to is a nice, rather simple expression for the root mean square velocity. And bear with me one last step. I'm going to take this and do these substitutions here, going from molar to molecular. And then we can write this also in terms of molecular counting. Okay, so let's just pause and make sure that's pretty clear what we've done. Here's our result from kinetic theory. Here's our ideal gas equation. Now just expressing P, the ideal gas equation, equating to this. The equivalence, this gives me a simple relationship now for the root mean square speed. What does it depend on? Remember, first off, we're looking on a molar basis. It depends on the mass of the constituents. Again, molar mass here, ideal gas constant. But most critically, it depends on the square root of the temperature. Okay? So, now we've learned this very important sort of simple relationship between temperature and molecular or constituent speed. And then doing those substitutions there allows us to do this actually in molecular terms. R and N become K and little m respectively. So that is, I would say, perhaps equally important result compared to our primary one, namely that our temperature is dependent on the square of the velocity of the constituents. So now we've finally got something quantitative that allows us to relate the microscopic behavior. What is it? It's just basically the speed of the constituents and what we're calling the temperature of our gas. So let me just highlight this, and of course we start off from here. Okay, quick comments or questions on that? Okay, so take a look at this. Maybe not easy this, but maybe even without plugging in some ballpark numbers. Let me ask you to give an educated guess, hopefully, about, or let's say some gas, standard temperature and pressure. So 0 Celsius, 1 atmosphere pressure. What sort of RMS speed might you, educated guess, expect for the constituents of a gas at standard temperature and pressure? No? Do your mental calculation. Thoughts? Huh? 16 meters per second?
Yeah.
Okay.
It's about 500 meters.
No, that's not crazy. Go ahead.
It's a little bit more than 500.
Okay, there was another hand up there. I just want to get another input. Okay, I don't know if any of you actually plugged in some numbers quickly. But you're all not crazily far off. Yes, typically for gases at STP, standard temperature pressure, we're looking at movement square speeds that are order hundreds of meters per second to maybe kilometers per second. For those of you who gave a number, I'm curious, some of you might have done a quick calculation, you might have looked it up, but was there any other piece of information that you might have fed into your guess, your educated guess? Anything you know that might be relevant here?
Doesn't it depend on doesn't it depend on the kind of substance? So they would have different molar masses?
Yeah, no it does, but again, for a typical gas at STP, so of course there's a range, but it's very explicitly dependent on this. But anything that informed your numbers there that might be relevant? I'm sorry?
Just assume that we were at standard temperature.
Okay, I'll push you a little bit more on this. What do you know about, I don't know, day-to-day experiences that might be relevant to what we've just determined?
I mean, most normal speeds we walk, fully super fat gas. So, if I walk at, I don't know what a normal walking speed is in meters per second, but, I'll just say 1 meter. Okay, 1 meter per second walking. I don't, disrupt the air. I don't feel like you'd disrupting the air. So, it obviously has to be moving pretty quickly at that.
Okay.
Yeah.
All right. I'm okay with that. Anything else? Yeah. Okay, here's one useful ingredient, speed of sound. Okay, we haven't talked much about sound, I guess really almost not at all. How is sound transmitted? Through vibration of molecules, sure. So the reason you can hear my voice right now is there are air molecules vibrating back and forth. As my vocal cords vibrate, they start to make air molecules vibrate, and you could imagine, conceivably, depending on the density of the gas, which we're going to talk about in a moment, you could imagine that individual molecules are kind of moving at around the speed that we've just derived. In practice, it's a little more complicated. The gas is usually dense enough that the molecules are colliding with their neighbors and transmitting the information from one to the other. But either way you look at it, the speed of sound is presumably relevant to this, okay? So it's presumably ballpark same number. What is the speed of sound at standard temperature and pressure?
343 meters per second.
Pretty close, yeah. So it's not surprising that we're getting a number that is comparable to the speed of sound in a gas at STP, okay? Anything else in your day-to-day experience that might be related to this? This is a little bit more subtle one. but not so much sound. Anything else that you might be aware of in day-to-day experience that is presumably transmitted by things moving at whatever speed we just derived? Smell. Good one. Yes. So, in fact, again, sort of similar to the idea with sound. Basically, that's probably more of a diffusion process than a transmitted wave, but you can gain some insight in how quickly molecules associated with smells are transmitted in a volume of gas by knowing this number, okay? So there are a bunch of everyday experiences that are in fact informed by this. All right, good. So speed of sound is probably the most relevant one. What else can I tell you about this? Well, in a moment we're going to address this question of how densely packed the constituents are in typical gas. But it turns out, just so you know before we do a quick calculation of it, that the mean free path, the average distance between collisions in a gas like this, is of order maybe microns, micrometers, 10 to the minus 6, 10 to the minus 5 meters, okay? So, think about this now as your maybe new picture of what the gas looks like. It's got these constituents that are moving at about these speeds of hundreds of meters per second to kilometers per second. But pretty much every few micrometers, they are bumping into their neighbors, they're bouncing off them, searing with elastic collisions. That's the picture I want you to have in mind now for gases at the microscopic level. Okay, so Noah, you raised the question importantly of the fact that the mass is in here. So it's 1 over the mass, and in fact it's square root of 1 over the mass. What does that tell you, obviously, about the dependence on mass? Which type of constituents move faster?
Smaller ones.
Small ones, okay? Here's a general piece of information. What's our atmosphere primarily made up of?
Nitrogen.
Nitrogen. What else? Okay, good. Trace elements, CO2, argon, maybe a few other things. What other gases are, let's say, common in our day-to-day experience, but apparently not common in our atmospheric makeup?
Helium.
Helium. Interesting. Anything else? Water vapor, sure. I mean, there's sort of smallish amounts, or depending on the weather conditions, smallish amounts of water vapor. Helium, anything else in terms of kind of common gases that we are used to, but apparently don't appear in the atmosphere? I'm sorry? Well, there's some of it in the atmosphere. Yep. Hydrogen. Okay. So, I know that was not the easiest sort of thing to be heading towards, but what's special about hydrogen and helium in terms of this?
They're very small.
Very small. What's their RMS speed as a result? The person behind me was doing something interesting. They're fast. Okay. Why might there be no apparent helium or hydrogen in our atmosphere? Awesome. Yes. The speed, average speed of hydrogen and helium is faster than escape velocity on Earth. So, I'm just going to stop rambling and get back to business in a moment. For example, many of you know there's kind of a pending helium shortage in the world. Helium is mostly extracted from underground reserves, which are very rapidly being depleted. When you guys go to the store and buy those funny helium balloons, of course eventually it diffuses through whatever it's in, or maybe you can release it, and eventually that helium goes into the atmosphere, and after some time it eventually escapes the atmosphere. So we really do only have, more or less, a finite supply of helium, and the same is true of hydrogen, because it has an escape velocity which is greater than the escape velocity on Earth. So any hydrogen and helium in the atmosphere will eventually go off into outer space. So, okay, let's get back down to something a little bit more, more quantitative. Okay, so now we've got this relationship for root mean squared speed. Let me could just go on a little bit here and talk about kinetic energy. Okay, so average kinetic energy, I'm going to write it as 1/2 mv squared averaged. So let's do that. Obviously, the mass, if we're looking here at a constituent, is whatever it is. So I'm going to bring that out and simply now make the average of the v squared. And so our kinetic energy is just 1/2 mv RMS squared. Okay. Now we already know RMS velocity over here, so I'm going to substitute for it. So substituting for the RMS from over on the left-hand board, and what you'll find now is that the average kinetic energy is 1/2 m 3 RT over big M, which is now 3 RT over 2 NA, our usual use of this conversion factor over here, and the other one also. And so if you allow me to make use of those, what you will find is that I can now write the average kinetic energy is 3/2 AT on a molecular basis, or a average equals 3/2 nRT on a molar basis. So molecular molar counting basis. So, no big surprise, because we saw this relationship between V and T over here, and we know how K depends on V. We get this very simple relationship between temperature and average kinetic energy. So now finally we've learned some important relationships, first off between pressure and speed, and then we've got this direct relationship between pressure and temperature, and then of course since we have that, we now have the relationship between energy and temperature. So, when we think about the kinetic energy of a gas, all we need to know is its temperature, and pretty much we're done, okay? So kinetic energy is 3/2 kT on a molecular basis. Questions or comments? Okay, say that again.
Is the RMS versus
Versus,
average, the average?
so, okay, so the RMS, so root mean squared. So you've got a distribution. You take your individual velocities in this case, you square each of them, you average them, and then take the square root. So that's what we mean by the RMS. And so that's basically what we're doing here. So that in that sense, these things are of course equivalent. Okay, good. So we got the key results in hand. Let's go back and look at this question of this mean free path distance between constituents. This is a fairly technical derivation, which we're not going to do. It's also not covered in our textbook. That's fine. All we care about is the result. Okay, so basically here we're talking about the average distance between collisions. Again, the derivation. So usually introducing things without the derivation is rather unsatisfying. I'm well aware of that. here is key dependencies on this mean-free path. So mean-free path, lambda, can be derived for an ideal gas under the approximations we've assumed, a couple of constants out front. And then we've got two key parameters here. So this is clearly a density. And over here, we've got the molecular diameter, or the constituent diameter. Okay, so this is exactly the same thing, but all I've done here is take pi d squared and just define it as sigma. And if you think about this, of course, it's nothing other than a geometrical cross-section. Pi d squared. Imagine these constituents just as being targets, and you've got molecules kind of aiming for those targets, the cross-sectional area. Just pi d squared, so we'll often represent this simply by sigma. So does it make sense? Yeah, I would say so. Again, no derivation, so it's a little bit unsatisfying. But as the density goes up, so the number per volume, as this goes up, the mean-free path goes down. No big surprise. The bigger the density, the smaller the mean-free path. And also plausible that for the larger cross-sectional constituents, then again the mean-free path goes down. You have a bigger target cross-sectional area. Okay? So this is at least plausible, and actually a surprisingly simple result. So again, if you were to plug in some typical parameters here, you're going to get numbers out that are of the order that we talked about, sort of micron-ish for gas at standard temperature pressure. That's what we talked about a few moments ago. Just to drive that home, and particularly independence on the density. So for gas at STP, lambda is of the order of microns, micrometers. If I was instead to go, let's see, I wrote down some numbers here. If I was instead to go to high altitude, maybe as high as 100 kilometers, that's obviously high. And in terms of density, many of you know the atmosphere really doesn't go more than sort of 20 or so kilometers in terms of where we really think there's any sort of finite gas left. If we go already to an altitude of about 100 kilometers, it turns out that lambda in this case is already of the order of tens of centimeters. Obviously there's still some gas there, but the mean-free path is pretty long. Yeah?
So in that N over V, what's the N?
Just the number of constituents.
Does that still count as a density if it's not a mass type thing? Or?
Yeah, I mean, in terms of cross-section, okay, number density.
Okay.
In terms of cross-section, all we care about is how big things are and how close together they are. So the mass, in this sense, doesn't really feed into the path.
And then it's not moles; it's just the number of atoms.
It's just the number, yeah. So, number of constituents. I mean, in a sense, you can use whatever counting you want here. You just need the appropriate conversion factors. Okay, so now we've got some idea of mean-free path. What I want to do now is just turn our attention back to this topic of what about looking at the actual speed distribution in some more detail, okay? And this is the second time today where it's a little bit unsatisfying because we're not going to derive what is a rather complicated result. Just try and gain some insight from the distribution. Okay, so moving to more realism. So the actual speed distribution of our constituents. Okay, so I'm just going to write this up, and we'll talk around it a little bit, and then come up with some particular results. So this is credited to Maxwell, a name we're going to spend a lot of time later in the semester discussing, but primarily in the context of electromagnetism. Here it is. So let me write this up and then we'll talk about it. It's somewhat complicated.